Welcome to Embedded Edge with Nitin, a podcast that brings to life the stories behind today's embedded systems, technologies and products. It's the show where you'll hear from both engineers and executives on some of the most topical news and most pressing challenges in the world of embedded system design. Here's your host, Editor-in-Chief of Embedded.com, Nitin Dahad.
Hello, welcome to this latest edition of Embedded Edge with Nitin. In this podcast, I'm going to be talking to several people around the major IT outage that was caused by a Crowdstrike software update to Microsoft operating system-based devices, which caused a lot of havoc around the world. And we talked to people both around memory safety and compartmentalization, but also on the implications of this from a cybersecurity point of view. Just as background, the technical information that's currently public seems to indicate there was a page fault within the operating system's kernel. And this arose from an update to CrowdStrike's Falcon software, which allowed a meaningless pointer to be dereferenced. When you have a page fault inside the kernel, there's not a lot else the processor can do besides activate that infamous blue screen that many people saw. And I think we heard the official figures, 8.5 million Windows computers were affected, but judging by the travel chaos, the banking chaos, general IT chaos, it seemed like it probably affected a lot more. So in this podcast, I'm going to be talking to three people. One of them is, the first one will be Russell Hagar, who's the CEO and founder of a company called ViperCore. Now, they've been looking at new processor architectures, but actually one of the aspects of that is around memory safety and memory access and memory safe designs. So he'll be talking a little bit about the vulnerabilities linked to memory safety. And then I'll be speaking to another expert, David Chisnell, who is currently Director of Systems Architecture at another startup called SCI Semiconductor. But he's been involved with in cybersecurity research over the last few years with Microsoft, and also he's been working on something called Cherry, which is a project around ensuring digital security by design and memory safety. And he talks about memory safety and compartmentalization and the principles of least privilege. And then finally, I'll be speaking to John Moore, who's the managing director and founder of the IoT Security Foundation, but he's also on the advisory board of the Digital Secure by Design program. And he talks about how, at a higher level, what are the implications of this, and the fragility that we have with single providers, and whether we should be looking at policy and regulation around the ability for one single provider to be enabling cybersecurity. And also, I just wanted to give a shout out to Embedded World North America. This is the second international offshoot of the successful Nuremberg-based exhibition for embedded technologies. From October the 8th to the 10th, it will be possible to meet industry experts from all over the world and more than 150 exhibitors in the Austin Convention Center in Austin, Texas. We, as Embedded.com, we will be there. So we'll be there at the show, and we look forward to seeing you. Make sure to follow Embedded World and, of course, us. But Embedded World on Instagram and on LinkedIn, on their official channels, and you'll find the links to those in the write-up next to this podcast. So on to my first interview with Russell Hagar. I'm talking to Russell Hagar, who's the CEO and founder of a UK startup called ViperCore. Now, ViperCore has been covered by EE Times in the past, and talking specifically about a processor, but actually we also touched on memory allocation and memory safety, and I think Russell and his team have done quite a bit of a internal discussion about some of the possible issues arising from the Crowdstrike update, which has caused some consternation around the world. So, Russell, hello, how are you?
Hi, Nitin. I'm fine, thanks. Good to be here.
So Russell, just tell me, what are your sort of initial thoughts?
Sure, thanks. So ViperCore, as you say, UK-based startup. We're a processor company. We're bringing some innovative research into how to do memory subsystems differently. The driving force was looking at how we can remove some fairly substantial bottlenecks when running managed languages like Python, C#, Go, and so on. They do an awful lot in the background in software. We've seen that overhead be as much as 80% on some real world applications. And we take all of that out of the software, we implement it inside the CPU, and we see 5x accelerations on certain types of workloads. So that's what we're about primarily, is about increasing performance in the CPU. What we had to do in order to make all that work is we ended up redesigning how the memory subsystem works. So we've got fairly involved in redefining how the caching system works, how the actual pointers are being used across memory, how memory allocation is being tracked, and we're doing all that in hardware. So we created a different abstraction in computer science terms as to how the processor sees memory. And one of the things that spun out of all of that, as well as giving us the platform on which to build this 5x acceleration, one of the things that spun out was we can deliver things like memory safety. So the way that we do the memory, as far as how the processor sees memory, it becomes impossible to do buffer overflows or to have memory leaks. And the whole memory safety area is key to cybersecurity. One of the things we push heavily on the performance side. When we're talking to customers, everyone agrees that memory safety is vital, but actually the industry in terms of providing memory safety from the hardware is still in its early days. Languages like Rust try and do memory safety from the software perspective. They're very successful at what they do, but a software solution can never be totally all-encompassing. We don't really see commercial traction. We have interesting conversations, but at their own hardware-based memory safety is too early. At the same time, the industry sees it as huge. So of the whole category of technical cybersecurity vulnerabilities, the non-technical ones are when you put a password on a post-it note, but of the technical ones, the industry consensus is something like 70% of all technical vulnerabilities are linked to memory safety. So that's a huge area. And so our business is focused primarily on delivering the performance, but we have this side project of how we address memory safety, how we can support that. So when we saw the news on Friday about CrowdStrike, and we saw some of the screenshots that were going around, it set us thinking. So that was the sort of process.
Yeah, there's a specific one which I think is out on the Google on the internet. Basically, the stop code page fault in non-paged area, and I think that's what gave you the clue to what this might sort of point to, as it were.
One of our guys posted it on the internal Slack channel and said, "I don't understand computing anymore." Page fault in non-paged area.
So what does that mean? What do you think?
Well, inside the kernel, and this is clearly a kernel fault that's happening. Inside the kernel, you can't really do paging because if you're relying on the memory allocations being fairly nailed down. If you're in the kernel and you have a page fault, then where do you go? You can't return to the kernel because it's the kernel that's just had the problem. So it's had a page fault where you shouldn't be doing. You just cannot tolerate any paging areas. That's essentially what it means.
What's that caused by? Obviously, do you think CrowdStrike? Obviously, the first thing is they issued the update without testing it. Is that right?
Well, I think that's the industry-wide assumption. So what it looks like is it's a code patch, it's an upgrade, it's an update to threat coverage, which has gone out. It looks like it's a code. It's a live code patch, an in-flight upgrade is rewriting, updating the code in place. And it looks like it's just a classic problem of a pointer reference that's not valid. So the code gets to execute it, tries to access a bit of memory that it simply shouldn't be accessing, hence the page fault. How does that happen? We have to assume it's a process error. Some internal sign off, all the internal processes you go through, which presumably should be done 10 times over if you're actually talking about code that's patching the kernel. Anything that goes wrong in the kernel has got the potential to do a blue screen. Microsoft have said 8.5 million devices were affected by this, which is a huge number. The economic cost of that is going to be probably immeasurable. It's a process error as to how this got deployed. It can't be anything else.
That sort of creates the question, can you test for memory safety? And is there a certification that you can do before you issue these updates?
That's a really, really interesting area. The industry was starting to get going on this. So in the UK and also in the US, there's really interesting focus. You've got the National Cybersecurity Centre in the UK who've been pushing on memory safety for quite some time, and they've been championing a technology that's come out of the research community, out of Cambridge University, called Cherry, which has very strong memory safety capabilities. And they've been working with their colleagues in the States. And in fact, there was a White House announcement earlier this year advocating memory safety, and it actually name-checked Cherry, which is quite nice. Yeah. I think the problems we have as ViperCore when we talk about performance and we talk about memory safety is our customer base is interested in performance first and foremost. And everyone agrees that memory safety is important, but they've got commercial customers have got a dozen other cybersecurity challenges to worry about as well. So the industry has a question: how does it take memory safety into deployment? Should it be based around one particular technology? Should we as ViperCore be expecting the world to recommend us? I don't think that's reasonable. Maybe there should be some form of memory safety certification rather than a technology specific. I think that's probably the best way forward. I know from conversations we're aware of that it's not entirely clear how you can encourage industry to do that, and there are some live conversations going on as to how commercial entities can be encouraged to take this in place.
Well, Russell, thank you very much.
No, pleasure to be on. Nice to talk to you, Nitin.
I'm talking to David Chisnell, who is with SCI Semiconductor, a UK startup dealing with hardware-based security. Hello, David.
Hi.
So, David, you've worked quite a lot on a project in the UK called Cherry, but you're also a researcher at Microsoft before, and you've done through your career a lot of cybersecurity research and implementation. Just tell us a little bit about, in summary, quick background.
Yeah, I really got into security almost by accident. I was working on a lot of end-user programming things. And when you want people to adopt high-level, very friendly programming languages, you don't want to rewrite all your existing software in those. You don't want to rewrite FFmpeg, which has aggressively optimized and tuned video decoders in some high-level language. But you want to be able to use them without any bugs in those completely trampling over everything else you're doing. Mm-hmm. And so I rapidly reached the point where that kind of safe interface between all the existing lines of, we have something like 12 billion lines of open source C and C++ code, and probably at least that much in proprietary repositories. And when you want to interface between that and some new safe language, there really aren't the tools to do it in a way that allows you to retain the benefits of the safe languages. So I joined the Cherry project in 2012, and that was working with Robert Watson and Simon Moore at the University of Cambridge. I was leading the programming languages and compilers strand of that. So we were able to evolve what they started with, which was very much focused on compartmentalizing user space applications in the same sort of way that microkernels have with kernel space things, although not in as wide deployment as people would like. Their sort of starting point was you've got a web browser and it puts every tab in a separate process, for example, but that doesn't really scale. If you want to have 100 tabs open, you start to struggle on modern hardware. And one process per tab isn't actually the level of isolation you want. You want every image you decode to be isolated. You want every video you decode to be isolated. You want the JavaScript JIT to be separate from everything else. And then you want every JavaScript worker to be isolated. If you're looking at a website like Gmail, every single email that you open is logically a separate trust domain. You don't want a vulnerability in your web browser that can be exploited by one email to allow access to everything else. And so you really want to go from being able to build hundreds of isolated compartments to building hundreds of thousands of isolated compartments for this kind of software. Mm-hmm. And when you're trying to solve that problem, you rapidly run into the fact that isolation is easy, it's sharing that's hard. Now, if you want to run two workloads that are fully isolated from each other, run them on different computers. Solved problem. But if you want them to interoperate with each other, if you want them to be able to share data, and especially to share rich data like the DOM in your web browser, that's really hard. And if you want to be able to say, okay, well, you have a rich read-only view of this data structure and you can follow pointers within it, but you can't modify it. That kind of thing is just almost impossible to support on conventional hardware. And that was the kind of problem that we were trying to address with Cherry.
Okay, that's a great introduction. Now, I think you sort of published a blog on the Crowdstrike issue. I think it's partly around that you think around that compartmentalization and the fact that there isn't really that proper separation, but also it's a memory safety issue as well, I guess.
To a degree, yeah. And I think one of the problems that we've had getting traction with Cherry is that when you really dig into it, memory safety and compartmentalization are fundamentally the same problem. You can't. You can build memory safety without compartmentalization, but you can't build usable compartmentalization without memory safety. You need to be able to say, these two things are isolated, but they can share things that I, as a programmer, can reason about. And that's not this page of memory is shared between them. It's this data structure is shared between them. We're transferring ownership of this data structure now into this compartment, or we're giving this compartment a rich view of this data structure. So with the Crowdstrike thing, it was pretty much errors all the way down. I think, and some of the postmortems are still coming out, but it appears that the root cause was the use of an uninitialized variable on the stack, which, depending on how many times you've rebooted and what was still on the stack, would, with high probability, be an invalid access and would trigger a trap. And if you have Cherry and you're just using it for object-level memory safety, so that gives you any bounds error is detected. You can't inject pointers. If you're using one of the Cherry instantiations that has temporal safety, use after free is protected. You still would get that kind of trap. The question then is, how do you recover from that trap, and what is the blast radius of failure for a component? And the reason that this was so bad on Windows is that buggy code was running in the kernel. And so the blast radius is it crashes your kernel. And if your kernel goes down, you don't have anything else available.
Yeah.
The Apple version of CrowdStrike's product, Apple doesn't allow you anymore to load arbitrary kernel modules, kernel extensions, they refer to them as. And so you have to write this as a user space program that communicates with the kernel. So they have this level of compartmentalization that's built on top of conventional MMU separate address space models. So whenever the kernel needs to make one of the decisions that this kind of management tool would do, it sends a message to a user space program, which then does some computation and replies either, yes, go ahead, or no, sorry, this is disallowed. And if that user space program had downloaded the policy update and crashed parsing it, then that user space program would have crashed. But the kernel would just have said, oh, this other endpoint for this communication protocol I have has gone away. It wouldn't have been great for security because it would probably then have failed open and would have just allowed any operation, but it wouldn't have cost upwards of $1 billion worth of outage.
Yeah. Is there something that CrowdStrike could simply have done very simply to ensure that didn't happen, or is it just an extra sort of bit in the code that allows you to check for these things?
I mean, in CrowdStrike's specific case, it was incredibly embarrassing because the Windows NT kernel supports structured exception handling. And so a 3-line change to just wrap their parser in a try and except block and handle that and say something that we don't understand has gone wrong, we're stopping now, would have prevented it from crashing everything. In terms of properly architecting it, they really should, and actually Microsoft should expose hooks to do this themselves. But in the absence of those, they could load a kernel module that really emulates what the Apple version does and just communicates with an unprivileged user space program. So the Google Chrome team has what they call the rule of 2. And this means that they say you may have up to 2 out of the following 3. Thing runs with elevated privilege, thing handles untrusted data, and thing is written in an unsafe language. And I think from CrowdStrike's perspective, their policy updates were trusted. And so it just about met that requirement. It was running with elevated privilege and it was in an unsafe language. But generally, people interpret that deals with unsafe data to mean anything that involves parsing. And so if CrowdStrike had even just moved the thing that parsed the updates out of the kernel and into a user space thing that validated them and then gave the kernel a set of structured commands that were not in that arbitrary, you have to go and do a lot of processing to update sort of structure, that would have helped. But at the end of the day, it really comes down to the principle of least privilege, that you should always run any bit of software with the smallest set of rights that it needs. And CrowdStrike, in common, unfortunately, with a lot of vendors that refer to themselves as security product vendors, were not respecting that.
I think you within the organization are looking at some microcontroller type products to sort of come out to address some of these issues. Is that right?
Yes, that's right. So one of the projects that I ran at Microsoft was called Chariot, where we looked at the existing work we'd done on Cherry, which was largely focused on things from mobile phones upwards. So, a modern mobile phone is at least 2 cores, at least a gigahertz, 64-bit chip with at least a gigabyte of RAM. And we were looking all the way up to 128, 256 core server systems with a terabyte of RAM. But we wanted to see what could happen if we took the ideas from Cherry and tried to scale them down to the smallest possible devices. So things with tens, maybe hundreds of kilobytes of memory, simple in-order pipelines. And at Microsoft, Microsoft is not a microcontroller vendor. They have a bunch of products that use microcontrollers, and some of them are their own first-party silicon that have a load of microcontroller cores embedded in them. So they had some internal uses for this, but it really wasn't something that they wanted to provide as a product or even provide as a fully in-house, we maintain our own ecosystem for microcontrollers thing. And so that project was open sourced. That includes a formal model of the ISA as a RISC-V extension, the tool chain, the real-time operating system that was co-designed with the compartmentalization model, and a reference implementation of the core. And at SCI Semiconductor, we're building on top of that, and we're planning on shipping Chariot microcontrollers. So these things have a really tiny trusted code base. The only thing that is really trusted for confidentiality and integrity is about 300 instructions. And to put that in perspective, that means we have about the same amount of unverified code in our TCB as the SEL4 operating system does. And they claim to be a formally verified operating system.
Well, Good. And I know you don't have a timeline as yet on that, but we look forward to hearing about that, David, in due course. Thank you very much.
Thank you.
And now to my interview with John Moore, who's the Managing Director and founder of the IoT Security Foundation. So, John, you're not just on... this is something you've been doing for a while, and we've known each other over the last few years. And I think you're having your 10th annual IoT Security Foundation event this year. But you're on the Digital Secure by Design Advisory Board as well. And this is relevant for a really topical discussion around cybersecurity in the context of the IT outage caused by a software update recently.
Yes, absolutely. And of course, we've known each other for a while, as you mentioned there, Nitin. And of course, I come at the subject from the semiconductor stroke embedded system space. Right. And, we set up the IoT Security Foundation 9 years ago now. We're just about to have our 10th conference. But, we look at security in the round. And what I often talk about is security and how it relates to safety, because some issues in security manifest themselves as safety issues and vice versa. But when we start looking at the issues we're seeing around the CrowdStrike incident recently, what really struck me was that we kind of need to chunk up at a different level, because we're really looking now at risk and resilience of systems, because let's not forget this. Actually, we'll be kind and we'll say this is just, we won't assume anything. I mean, it could have been someone inside the organization doing this maliciously, but let's just assume that they didn't. So what it shows us how fragile some of our systems are. And what struck me was that if you look at the impact of the incident, I mean, there was quite a lot of social impact. I'm sure we'll get to the economic numbers, but fundamentally, this was an accident. And as far as I can make out, it was an accident waiting to happen, because if you start looking at the specifics of what happened, there was a file which was read in to a piece of software which had privileged access, but the data file itself was changing quite regularly by the very nature of antivirus. And so this must have been known that it was a risk. So you start to ask yourself more questions, and I think where we could be specific, or the actors involved can be specific how they close that loop. It kind of, for me, I start to think about bigger questions. So, for example, the impact that it had, we know that it was the Microsoft operating system, not all versions of it. And of course, what we know is that Microsoft has got a very healthy market command in both the industrial and enterprise space. So that puts a very large market at risk. But it made me think about, the different players that ought to have an interest in this. Yes, of course, those companies who use the systems, but in terms of a nation's infrastructure, shouldn't this start to get the interest, let's say, of government? Because if there's such a fragile mechanism that can take out a large part of operation of, as we've seen, travel and banks and whatnot, then it does beg the question, how fragile are we with a single provider effectively, where something like this can go wrong through nobody's malicious intent, but the impact it can have. So, there are more questions there.
Exactly. I mean, I think when I've spoken to you and many others on cybersecurity, one of the big things always comes up is resilience, and it shows also that part of the consideration of security is resilience, and I don't think that was there in this instance.
I think that was also striking, wasn't it? Because if you look at the nature of the failure, what it required was manual intervention.
Yes.
And obviously that's a lot of manual work. I totally agree. I think, when we look at these systems, as you know, we do an awful lot of thinking about being secure by design. And obviously we want to encourage a security mindset. But what we also have to recognize is what we want is not necessarily the way the world works. And the way the world works is more practically in terms of meeting product deadlines. And so quite often, yes, in a perfect world, we would do it this way. But in practice, we need to be a bit more agile in operation. So we can think about how we might prevent things up front. And as you mentioned at the beginning, I'm part of this program in the UK called Digital Security by Design, which is speaks a lot to that. But we also have to recognize that things can and will go wrong. So in that process, can we start thinking about, well, when things go wrong, how can we limit the exposure of those things going wrong? And once they have gone wrong, how do we recover quickly? So really just to underline the thinking around resilience.
Yeah. So what do you think is a takeaway from this? Do you think the work you're doing in terms of raising the issue of cybersecurity, and you've done a lot of work around policy and sort of helping governments policy documents on this, but do you think this takes the awareness to a new level, or is a space does it make people think, maybe we should start talking to our manufacturers and making sure they've got things in place to address security and all that?
I think so. I mean, obviously, we've been advocates for best practice ever since we started. And, one of the advantages of best practice is it moves quicker than standards and certainly a lot quicker than regulation. So, what can we learn and instill from best practice? I think specifically for the work that we do at DSBD and especially the Cherry program, and I will say that we're not completely wedded just to Cherry. There are other technical solutions, but specifically with Cherry, there were two aspects to this which I think would have made a difference, and that is the memory safety part, because of course what we know is there was a null pointer. I think we know this, by the way, from what I've read, there was a null pointer, and Cherry would have prevented that. But also what Cherry is known for is its compartmentalization aspects too. So you can put things in containers and very much limit the amount of damage that any poor software has. As mentioned earlier, I also think that this is a bit of a wake-up call for policy and for governments and possibly regulation. We really should be looking at the dependency we have on, a small number of providers. So it occurs to me that we might want to ask questions that says, once a provider gets above a certain level of market penetration, maybe they need to come under scrutiny a bit more tightly because of the impact that it can have.
Sounds like a Competition and Markets Authority subdivision.
I think so. I think there are questions. I mean, I don't really offer you any answers right here, but I do think it begs more questions. How did this happen? How can we make sure we're in a better position going forwards? And I think substantially, the key takeaway for me is we can't carry on like this. We know the world is increasingly interconnected. We know that software has been written and deployed in a certain way for a long time, but I think that has to change. Recognizing the impact that things like this can happen. And I would also reference, in the past WannaCry as well, what we're looking at here is not specific cyber attacks. It is kind of collateral damage to unfortunate events.
Well, John, thank you very much.
Thank you, Nitin.
Well, that brings us to the end of this episode of Embedded Edge with Nitin. I hope you enjoyed that, and I'll see you next time.